Hello, so what we're doing today is we're going to be looking at a time-dependent material energy balance for CSTR, and then we're going to code it and solve it and plot the time-dependent concentration and temperature profiles for the CSTR when the coolant is increased at 305 at time equals 0. So let's draw this out. We're going to have our tank, and it's going to have a stir with a flow going in and a flow going out. And since this is a overflow tank, we're going to have a couple assumptions here. So assumptions, and we're going to have a perfectly mixed tank where our volume is fixed and our concentration going out is the same as the concentration within the tank. So let's just label what we know. So we have a Q in, we have a concentration going in, and then we're going to have a temperature going in as well. Within the tank, we're going to have a fixed volume, a concentration, and then we're going to have a temperature. And then going out, since we have a concentration and we know it's the same as what's in the tank, it's going to be the same going out. So our out is going to be Ca as well. And in this problem, we know that we have a jacketed system. So this means we're running cooling water in this jacket to cool down the tank. And we're going to have that as Tc. So we're going to see how that pans out. And what we know is this is a first order reaction. So let's set what our reaction rate is going to look like. So we have K, which equals K naught times R to the exponent of negative E over RT, which is the activation energy, over R constant times the temperature. And this is going to help us with our material balance and energy balance. Let's start with material balance. So what we know is we have accumulation, which equals in minus out, plus generation minus consumption. Since we don't have any generation, we do have consumption, we're just going to have our general equation look like this. So let's start with our left side. What do we know? We have a switch colors real quick. So we have a volume, and then we have our concentration. And this just gives us how much moles, since our meters cubed cancels out for each side. So this is moles per meters cubed, and this is meters cubed. It just cancels out, so this shows moles. And since we're looking at a rate, we're going to look at time-dependent rate, so moles per time that's changing. And for our left side, we know we have an in, so we have our Q in, which is our rate, our flow rate, and we're going to multiply that by the concentration going in. However, we're going to also subtract this by the concentration going out, which is the same as what's inside of the tank. So we're just looking at the difference. This is a perfectly mixed tank. And so we have our in minus out. So we're going to be looking at our consumption, and this is going to be like the rate at which is being consumed. So what we're looking at is our volume, and we're going to multiply this by our reaction rate, and we're going to multiply this by our concentration, which gives us how much the reaction rate at which moles are changing, I guess you could say. Since this gives us moles after the meters cubed cancels out, and this is our reaction rate. So there we go, and this is what our material balance looks like. But we can also just simplify this down by taking the volume out and just dividing it over. So then we're left with dCA over dt, which equals Q in over V times the Ca in minus Ca minus K Ca. And then we're going to head over to our energy balance, what that's going to look like. So for energy balance on our left side, what we're going to have is, actually let's start with what we want. So we want joules per second, since we're looking at energy and we're looking at a time dependent way. So we want joules. So let's start with temperature. So we have Kelvin. We're going to multiply this by our heat capacity, which is joules per kilogram Kelvin, to get rid of our temperature, unit of temperature, and then we're left with joules over kilograms. So we want to get rid of this mass unit, which we're going to do with density. So that's going to be kilograms per meters cubed. That gets rid of our mass unit. And then we want to get rid of our volume, which is meters cubed, or our meters cubed. So we get volume, and since this is a depending on time, we're going to have dt, and since we're looking at the change in temperature, we're looking at dt over dt. And then for our right side, our in minus out, we're going to have our flow rate, obviously. And since we're looking at the temperature change, we want to look at the temperature going in as our flow minus the temperature going out, which is, again, same concept with the concentration. It's going to be whatever is in the tank, leaving the tank as well. So we're going to be looking at the difference between this. However, again, we want joules per second, and this does not give us joules per second. This is saying our flow rate is going to be meters cubed per second, and then this is Kelvin. So we need something in the middle to counteract that to get joules per second. So we can do our heat capacity as well, which adds that energy in, and we get rid of our Kelvin. And then if we do density, we get rid of our meters cubed and we get rid of our Kelvin. So if we do density and this heat capacity, we get joules per second, which is what we want. However, we haven't accounted for the fact that we have a jacketed system as well. So we have to look at the overall heat transfer coefficient multiplied by the temperature within the tank minus the temperature of the cooling water that's circulating through, and that gives us our difference. And we're using subtraction because we're losing heat. So we're going to have or heat is leaving the system, so we're going to have a subtraction. And then we're looking at an exothermic reaction, so we're going to subtract this by the delta HR, which is heat of the reaction. And since we're looking at how much material is in the tank itself and the rate at it being consumed, we're going to be doing the same thing as we did before and multiply this by the VKCA. And to simplify this, we're just going to transfer all these three variables over the other side. So we're left with dt over dt, which equals, so for this side, we get rid of our rho and c, so we have Qn over volume with Tn minus T, subtracted by, since we don't have any of these variables on this side, we're just going to divide this by all three, and then multiply this by T minus Tc. And then for this side, since we have our volume, we're just going to get rid of the volume and have HR over rho times heat capacity times the reaction rate times our concentration. So here's our two equations that we're going to be using for Colab. So let's get on over there and do that. Okay, this is the Colab coding section, and I've already written all of the parameters down. It is from this table right here. Figured it'd be easier just to have this video be the actual coding rather than me writing down a bunch of variables. But we already have that written, and we're just going to get straight into this. And oh, I also have this script right here which accesses a whole sheet of a bunch of imports and I guess SciPy scripts or whatever, and this just accesses that. It was given to us by a professor, so it just makes coding a lot easier, as we don't have to go through the whole hassle of putting each import down all at once. So that makes it a lot better. So let's just get right into this. So we're going to define our right hand side as usual. That's our time and vector. And in this case, our vectors are going to be the concentration and temperature. And then we're just going to also write down our 3 equations that we found. Yeah, I think it's 3. Yeah, 3. So our K reaction rate, so let's put that down. And I believe it's NP.exp negative ER divided by T. And so the thing with how we wrote this down is ER is already solved for since R is a constant and we have this value. We just put it as ER, but it's technically this should be in the denominator, but for the sake of code, it's not. And then we're gonna write down our material balance, which is this whole equation right there. So let me zoom out a little so we can see it. And I'm going to put this as DCA. And we're going to have Q in which I don't remember if I did Q in not or Q. Oh no, just Q. Divided by volume, and that's going to be multiplied by the concentration in minus concentration, and then all of that is subtracting the K value times the concentration, and then we're going to do our energy balance as well, which is that whole equation. So we're going to have our Q divided by V, and oh, AI helped us a little bit there. Oh, never mind. No, it did not. T in minus T, that is subtracting our U8 divided by our rho, I'm going to put that in parentheses, rho times volume times concentration, or heat capacity, sorry. And then, yeah, I believe I got those. Yep. Yes. And then that is TC, not apparently. So we're going to subtract that by our HR divided by rho times heat capacity, and that is multiplied by the K value times the concentration. And then we're going to return our DCA and DT values, since that's what we're looking for. And I'm just going to try and run all real quick, see if it all pans out. Oops. Okay, so there we go. Yep. Yes. All right. And then we're going to just set our tendency, which since it's in minutes, I'll keep it as 10. And then as for our t plot, np dot linspace 0, 10, and since we've been using 1000, I'll leave it 1000. And then our Yeah, I believe that's about it. And then we're gonna put in our res equals. Oh yeah, we're gonna use a little bit of a different line as before. So we're using sp.integrate because we also have to let it integrate. So need to change that up a little bit. So it's okay. Just we're going to just set our parameters. So 0 to 10, and then we're going to put in our I guess our initial parameters, I want to say, which is CA naught and T naught. And our method is, as usual, regal. And then our dense output will always be true. And yes, that works perfect. And that's pretty much about it for the, I guess, solving portion of it. And then now we need to just make our charts. So fig equals make underscore subplots, and we're going to have rows equals 1, and then calls equals 2. I think that's right, yes. And then fig dot add underscore scatter, and so equals CA, or no, equals T plot, Y equals CA plot, and then we have row equals, yep, and then row equals 1, 2. We also need to put in name, which is CA, and then which is T. I think that about sums it. That should, oh my. Okay, I figured out the little issue. So we forgot to do our res.sol, and tplot res.sol tplot, and I think this should, yes, there we go. All right, so this is our plot for 300 Kelvin, but we wanted to, as it stated in the problem statement, we wanted to see what happens when we increase to 305. So right now what we're seeing is we're having a low concentration. It increases, and while it increases, the temperature decreases. But let's see what happens when we change it to 305. Nothing. Okay, I did figure out the issue here. So I had this as a negative. So when we had it as a negative, it just didn't change even for when I changed it to 305. But if I change it to positive, we do get the graph that we're looking for. So a little bit about what's going on here. you're starting at steady state, and as the as you take away cooling water and the heat increases, your reaction rate like you're using up your reactant, and then you'll slowly start to or actually I guess rapidly start to have a slower reaction, and then when you put back in your cooling water, your reaction picks up and you have more of a reacting, and then that's where cooling this is where cooling comes in, and it decreases your temperature and reaction goes up, and then uh, the heat starts coming back, and it just keeps repeating itself over and over again. And this just kind of shows what the unpredictability of an exothermic reaction looks like. So yep, that's part C.